Hello again, everyone. Dr. Tom McNamara here for our course in college algebra. In this video, I wanted to show an example of solving an absolute value inequality. In the previous video that we posted for this course, we discussed solving absolute value equations. Now, for the solution to an absolute value equation, we would expect two solutions. And we discussed the two cases that you would need to look at to find those two solutions. Now, typically, the solution to an inequality will be an interval of x values, not a collection of just one or two x values that make this a true statement, but there's going to be a whole range of x values that work. Okay, so here's the general strategy that I like to use for solving these absolute value inequalities. First step is solve what I'll call the related equation. Solve the related equation. So hopefully it's obvious what I mean. If not, I'll just write it out and be explicit about it. So here the related equation is absolute value of 2x plus 1 equals 5. So as we showed in the last video, we would consider two cases. So we take this expression inside the absolute value. It could be equal to the positive version of what we have over here, or this expression inside the absolute value could be equal to the negative version of what we have over there. Now, if this statement right here is true, if 2x plus 1 really does equal 5, we want to get x by itself. We subtract 1 from both sides. 2x equals 4, divide by 2, and we get x equals 2. Over here, we get x equals negative 3. Subtract 1 from both sides. Negative 5 minus 1 is negative 6. Divide that by 2, you get negative 3. So those are the two solutions to the related equation. Now, so that's step one, solve the related equation. I like to make this chart when I'm solving these inequalities. Okay, now this represents a number line right here. So on my number line, I plot the solutions to the related equation. Now you have to put them in order, in numerical order, okay? The cases I looked at were here, and I got 2 and negative 3 as the solutions. Notice I put negative 3 first. If I'm on a number line, negative 3 is to the left of 2. Okay, so I plot my solutions on a number line. I'm going to pick a test point in each of these regions. So my solutions divide the number line up, in this case, into 1, 2, 3 separate regions. This region is everything greater than 2. This region, everything between negative 3 and positive 2. And this region, everything less than negative 3. We pick one representative from each region. Over here, I'll pick a 3. That's something greater than 2. Here I'll pick 0. I can pick anything between negative 3 and 2. Here I'm going to pick negative 4. So what I do is I take these test values and I substitute the test values into the original inequality. Okay, so let's use this. I'm going to test negative 4, and I'm plugging it in right here. 2 times negative 4 is negative 8. Plus 1 is negative 7. Take the absolute value of negative 7 and you get 7. 7 is not less than negative 5. So our test value didn't work. That means nothing in this region is going to work. Okay, let's use this test value. Test value is 0. 2 times 0 is 0, plus 1 is 1. Absolute value of 1 is still 1. That is less than 5. So the inequality is true when we use our test point, and that means it will be true no matter what we use in this region. Lastly, let's try this test value. Plug in x equals 3. Substitute 3 for x. 2 times 3 is 6, plus 1 is 7. Absolute value of 7 is 7. 7 is not less than 5. That region is out. So my solution set is the set of all x values between -3 and +2 for an interval notation like this. Okay, notice I have the parentheses rather than the brackets. I don't want this expression to be equal to 5. The inequality was less than 5. It was saying absolute value of 2x plus 1 less than 5. If I plug in -3 or 2, it would be equal to 5. So these points don't actually belong to the solution set of the inequality. So a very useful little tool here, this chart for helping us to solve inequalities. So the strategy is solve the related absolute value equation and then use those solutions to make your chart. You got to plot them in order. So remember, -3 is the smaller of the two, so that should be to the left. Okay? And then pick test points in each of the regions. And then take those test points and check them in your inequality. If they work, then that entire region is part of the solution. If they don't, if your test point doesn't work, that entire region is out. Okay, so very, very neat tool here. I'm also going to show you another idea that can help sometimes. So we got the chart. An alternative to doing the chart is working on solving these things graphically. Okay, now in some previous videos we have discussed how to graph absolute value functions. All right. So what I'm going to do is I'm going to start by graphing absolute value of 2x plus 1. So okay, this is part of the graph. Now, if I were to just graph 2x plus 1, it would be a line, y-intercept 1, slope 2. So if I increase x by 1, I increase y by 2. All right, so this line would continue down here. But if I take the absolute value, I'm not going to get any negative y values, I would get positive y values only. So you might want to review the video that we posted concerning graphing absolute value functions with reflections. And that's how we get this right here. Okay, so got an absolute value function, so we see this V shape, and there we go. Okay, now, this by itself is not going to help me solve the absolute value inequality. I need to graph something else. 1, 2, 3, 4, 5. I need to graph the horizontal line y equals 5. Okay, so we notice this intersects the V-shaped graph in two places. One of these places is -3, 5, and another place is 2, 5. Okay, right there. So we can see this graph, the graph of the absolute value function, is under the horizontal line between x equals -3 and x equals 2. And that's our solution set as we saw from the chart. Okay, so you can use the graphs that we've discussed to help you solve these equations and inequalities. Everything that we do algebraically is going to have a geometric manifestation in the graph.